Okay, thank you very much. Thank you for inviting me. Thank you for coming. It's probably my first public speech in Brno after 20 years. The previous one was my final exam at the high school. And also I looked at the previous topics of the machine learning workshop, and it was everything so deep and like smart and clever. Well, today I'll speak about something rather, oh, sorry. Okay, that's not working, sorry. Rather simple, and that is time series and time series analysis. So time series are just bunch of the observations measured at the regular time point. And you do nothing complicated here, you're just trying to draw the lines through these points. Based on your style, you can select what you want to do. And usually slightly to the right, to the future, that's the forecasting, and that's all the fun. It started in the 70s. The theory was originally developed mainly by econometricians, so it was classical statistical models. Well, if I'm asking this crowd, like, what would you use for the forecasting, the answer would be, you know, machine learning. And that's creating some tension because the statistical crowd and the machine learning crowd is speaking slightly different language, using slightly different tools, and there are people that are trying to connect that. This is from the last year, from the journal PLOS One, one of the most accessed papers of 2018. And the reason why it's most accessed is that the result summarized by one of the authors in this tweet was kind of controversial. He claimed that the best machine learning method did, by his testing, worse than the worst of the statistical ones, and half of the machine learning methods was basically the random noise. And you know, is it correct? In a way, yes or no. But about this controversy, about this, let's say, tension between the classical statistical word and the new machine learning word will be this talk about. If you are speaking about something controversial, it's good to say who you are. So my path to time series is actually not so long. I would not call myself an expert to the time series. It started during the snowstorm. As Pavel told, so what's my original background? My current job title is machine learning engineer at CAI, but I spent most of my life as a statistician. I've got a PhD from Charles University in Prague. I was working most of my career as a biostatistician, so that's a person that is connecting the biology word here and with the statistical methods and computational methods there, translated in both ways. And I was not really needed time series because I was mostly working with mice, and mice do not live so long. And that time, during the snowstorm, I was in US. I was living, I was working for the Jackson Laboratory, which is a small lab in Maine. Maine, for those of you who do not know, northeast corner of the United States near the Canadian border. And most of my colleagues didn't arrive to work because it was basically, the snow was falling so heavily that they were afraid to be stuck on the road. So I was there, nothing much to do, reading the Facebook, most of my Czech friends posting the spring photos on the wall, and I was kind of unhappy and thinking like, oh, I wish to be somewhere where it's warm, and fill in some small form. And 2 months later, I was here in California interviewing to Google, and when they accept you during the time matching phase, you basically speak to several team leaders, trying to find somebody who you can who you understand with. And I was interviewing also to some team series forecasting group, and I openly admit, like, you know, I've never done time series. I've done like many parts of the mathematical statistics, but never time series. And he said, you know, you could learn that. And that's what kind of happened. So a very small legal disclaimer, I've signed some NDA, there are some technical stuff I can't disclose. If you feel I'm saying something that I should not, I would be more than happy if you tell me after the lecture. But I can tell like everything that was made public, and I'm lucky here because about our time series tool was published a post on something that I don't know how many of you know, the unofficial Google data science blog. You can Google that. So I can share like everything of what's in this blog post, which is almost everything. So just to tell you what I mean, when I'm telling the time series, what do I really mean? Because there are many of them. So if you look at that, this is actually, because I can't share Google traffic data, so this is the Wikipedia traffic data that is public. So it's some web page about the Halloween on the French Wikipedia. On x-axis you have the date, so it's a daily data. Each observation is 1 day, and it's roughly 2 years. On the y-axis you have number of the accesses, and I would just like to stress that it's the log 10 value. So if here is the 3, it means that it's 1,000 for 10,000 to that we are in the hundreds. And at the end you have forecasts from 5 different models. You can see them, like some of them totally nail it, and some of them are totally off. Okay, so if I would give you, maybe I should also stress like what's specific about those data. If you look at that, you have some annual pattern. The people are reading about the Halloween, if it's around in November when it's around the Halloween. So that's first pattern you should see. The second pattern is those up and downs very frequently. Does anybody can guess what it is? Yes, that's the weekly pattern. So this is clearly like the human-driven data set, and that's quite important. Another thing, if you look at that, it's well predictable. If you look at the amount of the noise, yeah, there is some, but it's not like the big one. So it's very different if you take the data like the share price that are very hard to predict because it's jumping up and down. This you can roughly say like what it will be. So some naive models you can think about, like if somebody will throw the data at you and you would knew nothing about time series and time series analysis, like what's the naive benchmark you can try to quantify how much better is your model. So the most naive one, you take the last observation and you predict the flat future, these observations forever, or you take last few values, 2, 3, and you just do the regression and draw the line again to infinity. Can anybody come with some other naive model that would be better than that? Any ideas? Average, yeah. You can do the average, but if you look at that, the average would be, I don't know, somewhere here. So maybe it would not be. Like, think about the short time forecast, like the next week or next month of the data. What can you do? Exactly. That's exactly what, you know, what's another good naive benchmark. you can try and you should try, and you will see that these naive benchmarks can sometimes be better than very complicated models. So you can copy the last year. I'm sorry, this is me drawing. So just take this and copy it again, or take the last week or month or something like that and copy it again. Okay. Some simple but not so naive models could be some moving average, some exponential smoothing, ARIMA models. If you want to start with the time series analysis, this is a really good book from the Rob Hindman, especially if you are not so much interested in the mathematics, you just want to do that. So this is the no fuss. Of course, there is some mathematics. You can't do time series with no math, but it's more like software computational oriented with code and everything. If you are Bayesian statistics, there are many good papers about Bayesian state time series. Actually, this is another post from the Google data science blog. Just to show you that in R, it's just to do those simple models, it's just 3 lines of code, and it's running very fast. So if we want to do that, you can. In Python, it's statmodel.tsa, but honestly, the most of the researchers I know in time series, it could sound surprising, are still using R and not the Python. That's one of the exceptions to the rule that now everybody is adopting Python. Time series are the exception. Okay, so what have we done at Google? So this is just copied, I have copied the schema from the blog, and now I go step by step. So if I have the time series is here, the red line. First, I have the daily data, and the first step is the cleaning. I'm cleaning 2 things, the anomalies, like, this upward blip, and the level change, or you might know it as the change point. Basically, you are here, then somebody redesign your web page or add a new feature or something, and it's like jumped up. So for the analysis, it's good to like remove both those anomalies and those level changes. So you basically, this is the input, the red line is the input, and the green line is the output. So this was removed, and this was shifted upwards. Okay? So the second thing is the holiday adjustment. What's the difference between the holiday and the anomaly? First of all, holiday effect is something you want to keep, that's the real thing. And the holiday is something you will see, every holiday. Those are probably Christmas, if you look at that, it's the end of the year. But some holidays are a bit tricky. Think about the Eastern or the Chinese New Year or things like that. And honestly, I believe that the good value of the software is that like many of the time series, if you are the engineer, you can come with some forecasting tool, but the holiday and holiday adjustment is one of the things that is like not so easy to implement in a short time. If it should be like any holiday, anywhere on the world, you need some good database. Plus, if you have the summertime, your time series forecasting, if it's human-based, probably change with the summer and the winter time. If it's daily data, it doesn't matter so much. If it's hour data, then it matters a lot. Sometimes you have February 29, so one of your month has extra day. Ugly, but unfortunately it happens. Okay, so this is basically shifting the line to be all the same, recording those holidays. So this is not removed, but it's like recorded like this big change is probably Christmas. Okay, So then we do some seasonal decomposition. I've changed this time series, sorry for that, but if you look at that, you can clearly see, first of all, the weekly trend going up and down, and the annual trend, like this pattern is repeated here. Okay? So we are trying to write this time series as a sum, decompose it to the sum of several time series. So this is the original one, just a bit squeezed. This is the annual pattern. So this is what's repeated on annual basis. This is the weekly pattern, so just 7 days, up, down, up, down, up, down. And this is what remained. And you can see, you know, it's not so hard to predict something like that. It's just some linear trend, so I can write this one down as again as a sum of two. So one is clearly the linear trend, and the other is what really remained. And the good thing, if you want to do the forecasting of this, like it's easy, it's nothing complicated to forecast this, because it's periodical. This is also periodical. Theoretically, you can have even more seasonal components, like if it would be hour and not day, then you will have some seasonal component of the day. And then you have some reminder that you really want to model. Okay? So we don't have one model in this. At Google, we have like ensemble of the models, I believe more than 30 of them. And so what each of them is doing is taking those data and provide you some forecast. And at the end of the day, you summarize those forecasts, traditionally doing something as simple as median or average. Okay? And at the end of the day, you aggregate the forecast, as I've said. You somehow add the seasonality and the holiday back, and you've got your forecast. I know it's slightly too fast to go through all that, but if you think about that, it's really about the decomposition. You think about your time series as a sum of the seasonal component, or components, then maybe a trend component, and then what everything's left. Okay. So if it works, it's great. If it doesn't work, it looks like that. You have something in the middle that probably was not cleaned as the anomaly, and thanks for that, your like daily effect was clearly overestimated, and like you've got the forecast, the orange is one forecast, the purple is another forecast, that if you show somebody, he will be like not very happy. And it's unfortunately happening from time to time. And people usually comes with the time series where you provide some really shitty forecast. And like another thing is that the time series ended here and your forecast continue like way up or way down. That could happen, for example, if you misled the level change and the annual pattern. You know, if the time series forecasting thinks that this was the annual pattern and it was actually the level change, it will repeat it in your forecast, and that's why you are off. Sorry for that. So the Google never open sourced the internal forecasting tool, but Facebook did. 2 years ago, it's called Profit. You can see that like the math is similar. It's decomposed time series into trend plus seasonal plus day of the week plus holidays. It provides some list of the holidays. I actually never use it, but I want just to state it that this is something that you can come home and use. There's the package both for R and Python, so no matter what you prefer, you can link to it. And yeah, But back to the controversy, it's actually nothing new in the time series business. It was here even in the 70s. And it is, by the way, the same professor that sent the tweet was unhappy at the 70s because at the time something that was called Box-Jenkins method, today it's usually more known like ARMA or ARIMA, there was some hype around that. They finally solved some theoretical problems and everybody was trying to use it. And he was like, yeah, but if I look at the practical data and I take the exponential smoothing, this is the most simple version of the exponential smoothing, there are more of them, but it's, it's basically two equations, it's the ugly engineering hack, but he was giving better results from the exponential smoothing than from Box-Jenkins methods, and nobody believed that. So, because he was so unhappy, he said like, let's make a competition. And that day, it was competition more like between the methods than between the people. So he convinced the postdoc, I'm not sure whether Box or Jenkins is postdocs, to like provide him the forecast first for 100 time series, and that was the M0 competition. And when they were unhappy, they expanded that from 1,000 time series. And if you look at the results, it was like quite clear that the exponential smoothing did a better job on the practical data than the ARIMA model. So he kept doing those competitions roughly one every 10 years. So I skipped the M2 because it was not really about the time series. This is M3 when he takes 3,000 of the time series in 1998, send them to multiple people and ask them to provide forecasts. The winning solution, what's quite important to say is that the time series were taken from many areas. There were some business time series, demographic time series, finance, economics, whatever. So you have to predict like one time series at a time. The winning solution was something called TEPA method. You might have heard of that. And the original paper was quite complicated. It was really heavy to read. But later, like in 5 years, they showed that the method is equivalent to basically taking some weighted average of linear regression and exponential smoothing with the drift. So it's not so much complicated after all, but there was many controversy about this time series. Basically, the people debate that time series from the beginning, including the tweet you have seen. The problem was that they were thinking like, first of all, like, you've selected some time series. What if it depends on the kind of the time series you've selected? And of course they were right. There was a possibility of the cheating because the time series were real data. So if somebody, was highly motivated to be good, he can find the time series of the actual data and then basically copied the correct answer. Not all solutions were open. For example, the second place was some commercial software which never showed the source code, so who knows. Somehow the numbers didn't match. Somebody repeated what they claimed and claimed that the matrix is not correct. But the databases was used for another 20 years at some golden standard, like if you come with the new method, how are you doing on the M3 database? Okay, M4 competition was something that happened last year and was they try not to do so many mistakes like on M3. So first of all, they were much more time series to make it harder for somebody to find them. They have more types of the time series, so not only monthly, quarterly, but also hourly, daily, and weekly. They asked, somebody was saying that, okay, you have the points estimates, but what I really care is the interval estimates. So they are now asking both for points estimates and interval estimates. And they force everybody who want to compete to put his solution on a GitHub in some way that can be reproduced. So the method must be public. It can't be like private solution. And what might be interesting, like on the machine learning meetup, is that the winning solution this time was a combination. So the pure machine learning solutions on that competition didn't do really well. So, which is a chance. If you think that you can do the good prediction of the time series, and if you really could, then you can publish paper and be famous. But so the pure machine learning solution didn't work, and the king was the combination. From the 17 best solutions, 12 in a way combined some methods. So the winning solution from the Slavek Smil from Uber combined the recurrent neural network and the exponential smoothing. It was working, I don't have time to go into the details, but basically the recurrent neural network was running through all the time series, and the exponential smoothing was like transforming the time series into the same parameter space. If you want to read more about those M competitions, that is preprint from Rob Hindman. If you go to his webpage, I guess there will be some publication. Is not yet really published. So I mentioned deep learning. Deep learning or recurrent neural network. The deep learning and neural networks revolutionized many areas in the last few years. So image recognition, audio recognition, text, natural language processing are now mostly done through neural networks. Which is, if you think about that a bit unintuitive. I'm saying here, like, with the neural network, I can do awesome stuff like that, and I can't draw the line through a bunch of the dots. That doesn't make much sense. Why is that? First of all, it's not true that I can't do that. I definitely can. If you Google like using recurrent neural networks or LSTM, which is one kind of the recurrent neural networks, for time series prediction, you've got the hundreds of thousands of the hits, and on most of them you've got some intro, like possibly with the code, how to do that. The trouble, or what I have found troubling, is that most of those never compare their solution to the simple benchmark. Some of those data are very hard to predict. If you have, like many of those I have seen, like predicting the S&P 500 share index, this is very hard predictable. So you can't really see like what's the quality of those predictions. You see something on a graph, but whether it's working or not is hard to guess. So I want to get to the point why is it so hard. And I would like to point that in M3 or M4 competition, the time series were really difficult, really different, so you predict one at a time. This is some of my code that is adapted to some other code based on the keras that I'm using for time series prediction. And if you look at that, so I have like 200 units in the first layer, 200 units in the another layer. So even just first two layers, you have something like 40,000 parameters. I said we are measuring usually the daily data. You have 2-3 years, so 1,000 numbers. So based on the 1,000 observations, you are trying to fit 100,000 parameters. That is really hard. Like you can do some regularization techniques, but it's really, really hard. And I believe that's like the reason why for some sets of the time series, the machine learning methods and specifically neural networks are not doing a very good job. That's just my story. I don't read a paper that's claiming that, but that's what I think. And actually, if you go to the Kaggle, many of you know the Kaggle as the server for the machine learning competitions, but it's also a good source of the open data and the Jupyter notebooks or R markdowns documents above those data. You really see that it depends like on some of those data. One method is winning, and on the other one is winning. And I want to talk mostly about the last one, so something I've already mentioned, the Wikipedia web traffic forecasting. Let's look at that. So it was the competition. Now there's a data set. Each time series is one Wikipedia page. I simplify here a bit because there are several languages and so on, but for the simplicity argument, imagine that you have one Wikipedia page and you are trying to forecast the traffic. And you have 2 years or slightly above 2 years of the observations, and you are trying to do the following 2 months. They really do it in a way that they ask the participants, like they've got the data sets and they've got like 2 days to predict something, and they waited another 2 months to get data collected. The metric that was used was Snipe. This is like this is the actual value, this is the forecasted value, so you take the difference and divide it by the mean. By the way, the metric really matters. You've got different results for different metrics. This is called S-MAPE, this is symmetric MAPE, but it's not very symmetric. It's cheaper to overestimate than to underestimate. If you use MAPE for throwing a dice, then the best value to forecast is 4. It's easy exercise, you can try that at home, but you would guess that it would be 3.5, like the average of 1 to 3.56, but it's not, it's 4. Okay? So some of those time series are really unintuitive. Look at this one. There is some nice weekly pattern, then something happens, and people start to care about those Wikipedia page. It's jumping up and down. This is, by the way, not on the log scale, and probably should be. Okay? So let's first look at the results. From top 8 methods, 7 are neural networks. As the exception, there is one very smart statistical one, Kalman filters applied in easy way. So it's not that neural networks totally win, but they clearly win. This is the recurrent neural network, this is just some dance. Some of those solutions could use some random forest in the middle, but it's more like to mix several solutions that are neural networks. The random forest, by the way, didn't do pretty well, and also the Prophet, that was like the first solution that many people tried, was like way wrong. Why is that? Like, part of the reason is what was shown on the previous slides. Like, this is not what usually statistical model is prepared for. The second thing is, if you look at the average traffic, you will see that only 20% has more than 1,000 visits. there are like many pages that nobody or almost nobody read, so the values are 0, 0, 0, 1, 1, 0, 0, 2, 0, 0, 0. And again, statistical methods are usually not prepared for that. But that's not an excuse. The loss function and the metric is clear, and the advantage of the neural network is that they were like much better than to adapt for that. Also, if you have the metric, you can game it. Like the big step that most of the participants found was that if you round the values, you go many places up on the leaderboard. And that is because if you have this 0, 1, 2, so the low traffic, you know, you get higher chance to get it exactly right, and that matters. I also tried something that I do not have on any slide, and that was, I've tried to select the time series that I was able to nicely decompose into those seasonal trend and noise part. And for those ones, the statistical methods were better. But it's kind of not correct because the neural network was fitting everything and then could like screw itself to fit here. But the biggest difference between this and all M3 competitions is that here you do not predict, or most methods do not predict one time series at a time. It took all 150,000 time series and predict them at once. And the advantage is that if you have relatively short time series, just to remind you that it's just 2 years of the data, then you can borrow the information between the time series. You can see the pattern that was already seen in one time series and learn from that. So once more, the difference here is that you don't have just 1,000 numbers, but you have millions, hundreds of millions, I'm not sure about. And that's the difference that will make deep neural network working. So as a conclusion, classical or machine learning methods, of course both, depends on what's your problem. And specifically for time series, statistical forecasting methods is great, especially if you have just a few time series and you have a long history. So if you have 1 or 10. Deep learning forecasting methods are great, especially if you have many, like tens of thousands, hundreds of thousands of short time series. The question, of course, is what if I have thousands and I have 3 years of data, and here I'm saying, I don't know, try both, you will see. So, yeah, this is my current approach. I'll just have some methods, and if I have enough of data, I can tweak parameters and measure the ones that is working. And that's all, folks. Thank you for coming. What are the questions?
So thank you very much for the presentation. Now we will begin the question session. Once again, you can ask the question on slide.do/MLMU. And yeah, we will swap the image to the question. So far, does anybody have a question from the audience who doesn't have probably access to internet or cannot ask the question online? Okay, so I will ask. Oh, nice, it's here. So the first question: what is the accuracy of human compared to the statistical and machine learning methods?
What do you mean by human? Like, you mean if I take the pencil and try to draw it through the points?
It's probably like before the computers were there, maybe some traders on the market or something?
I really don't know. It always reminds me, my friend after school started to work in the marketing, and he was saying like, those time series technique that I've learned for 5 years at Faculty of Mathematics and Physics were useless for her, because what really matters was asking marketing people for the TV ads, and that was really driving her data, not while time series forecasting was not working. So it really happens on the problem. I can imagine if you don't have enough data, if you have 2 years of the data, then maybe some human expert can totally beat the things. Otherwise, I don't know, sometimes you can guess, do some clustering thing, and that way you can get the expert knowledge. I mean, it really depends on what's the problem.
So you didn't use humans at Google to predict stuff, right?
That's interesting. We should, maybe we were doing that right, but I might not say it exactly, but the Google problem or Facebook or any big company problem is that you don't have one time series, but you have many of them, and you need to forecast them on the automated way. So I would even say that quite often it's not about to get the best forecast, but to get the solution that is robust, that will not go crazy. Yeah. That's what might matter more.
Okay, so when introducing the changes, discontinuities into the models, do you detect them automatically, or do you use human-provided information, or maybe combination of both?
Mm-hmm. So the anomalies are detected automatically. That's whole the point. But you of course use all your information you have. So if you have, for example, holidays are kind of the changes that you know and want to remove. Also, if you know about some level shift that you are deploy something, or then it's always good to check for that. And you might even do it automatically, but you probably want to check that it was really removed.
So you first check what's deployed on my service when the interface change or web page,
exactly.
And then you probably search quite semi-manually.
Yeah, quite often is that you detect that, and it's some big difference, and then you are looking for the explanation, why on the hell do we see traffic on totally different level?
Okay. And on your slides there was cleaning and then the holiday detection, and probably it's the other way around, I guess, because you could clean the holidays by mistake?
No, that's, by the way, excellent question. We have did both. I can't go here into the technical details, but I have seen things that are really tricky, in the forecast you have the Halloween peak, and the forecast looks good, just and that was because the previous peaks have been by the cleaning, shut it down to the half. So sometimes if the holidays or the anomalies are larger than you expected, or that you have the parameters in your model or in your method, it could be. So this is, by the way, excellent question. Yeah, whether first cleaning or the holiday, or how to do both at the same time, it's
the secret. Okay.
Yeah.
Okay. Why is Snipe used for Wikipedia prediction competition?
Because it's one of the loss function or the metrics on the market. So the people are either use Snipe because they like the word symmetric, even as I have said, it's not very much symmetric. Or they use MAPE, so that is just divided by the actual value, not the average. Or, but with each of the metric I know there is some issue connected. Other one is that people sometimes just take the difference of the log values and look for the sum of squares.
The absolute difference?
Absolute difference, of course.
So, because when we looked at the dice example, it really looked strange to the 4 is the correct value, right? So
no, that's like when
no hidden insight behind it. Just
I don't remember, but there is some like the same way absurd thing about the map. I would need to check myself. So it's the takeaway message is that it's really hard to come with a good loss function for time series.
Okay, so when we have 100,000 time series, does it make sense to have global machine learning prediction and then one for each of the time series, as in image recognition? It's a tricky. So anybody cares to dive into more details with the questions?
Is it like the fine-tuning? Because I would love to do fine-tuning with the time series. If this person is able to develop that, talk to me. I'm like really interested. Because think about it. That could be like really smart. If you have like big data, you can train your model, and then having just hundreds data sets, you can then fine-tune to those hundreds data sets. So
transfer learning from the global all of the time series of the world to your specific.
I totally love the idea. I have never seen that working.
Okay, so if anybody doesn't want to specify or get their answer, we can continue. Probably we can continue. So why CEAI instead of Google?
That's really easy. My family moved back to the Czech Republic, and I either have to divorce or like find somebody to employ me in Brno. That's as easy as that.
Okay, so what are the options for comparing estimating numerical value representing similarity score time series? Is there any way to tell the data is random?
I'm not sure that I understand the question. Could the author...
maybe to compare. So any specification of the questions from the audience?
Yes.
Oh, back there. I will give you the microphone.
Hey. So my intention is, for example, for clustering. I have many time series, and I want to know whether I can compare them so that I could cluster them. And if I could do that, maybe can I also tell whether the data is random and it cannot be compared in that way?
I'll answer first the clustering. That's excellent idea, and that's actually working really good. I didn't talk about that, but especially if you have short time series, imagine that you are eShop and you are trying to predict sales, and you have the new product, and this new product has only like 1 month of a data, which is of course not enough, but if you are able to cluster it to like another time series that you have that are much longer, you can do much better prediction. So the point for that, I still don't understand what do you mean by random?
It's a difficult one. Let's say I have some number of time series, and I want to say, okay, this time series does not appear to follow any pattern. I know if I could answer this question, I could say, yes, there exists a model that would predict that. Or no, there does not exist that model because the data is random. And the question is whether I can numerically evaluate how the data is random. I know there exist some tools like autocorrelation that can do some sort of things, but it's not enough.
This is really interesting. Let's talk about that after the talk. I'm probably, but that's really smart idea.
Okay, so you decompose the series to annual, the day of the week, and trend plus noise. How exactly do you extract the annual part?
Yeah, that's the good one. There are several things how you can do that. Honestly, my answer would be to call STL function in R, but that's like one of the choice you can do when it fit basically the loss estimator that will like remove the trend, and then you put different years on on that and try to find like common annual pattern. Because if you detrend the time series, it's as easy like plotting different years on the same graph and like averaging for each day of the year or doing something a bit smarter than averaging.
So you cut it to the separate years, then just overlay and find
this is just one of the possibilities. Okay. There are more of them.
Why isn't anyone making multiple models to vote for the correct answer or boosting?
They're doing. I've said that for M4, the top from the top 17 solution, 12 did some way of the combination. So sometimes it's voting, sometimes it's something different. There is some theoretical problem with that I don't understand. But for example, the reason why people are often doing the median and not something smarter is this. You can be easily wrong. Like the method that look good on the training data could be just because it has more parameters, so it's get like the stronger vote, but it's not so much doing well on the...
And that's basically what I understood from our slide that you did at Google, right? You had like many different models.
Yeah.
And then you...
But this was kind of the fixed. We have like we did something like the average median, and the weights were fixed. It was so we removed if the model was really outlying, if it was way much different than the other ones, it was removed, but otherwise.
Okay, and what about boosting? It's like kind of different kind of ensembling to repair the error of the previous models?
Okay, never think about it. That's like interesting ones. I would need to try. And definitely like go to the Kaggle dataset and try that. And if you are doing time series, I highly recommend the Kaggle dataset, because if your model is failing on something, you will find it there. It's 150,000 time series, and it will point a weak points of your methods.
So can you elaborate on data cleaning? How much do you use humans to clean training data?
So for the tool, or both Prophet and what I have seen at the Google, none. Like it's really automatic. You don't have enough humans to do all the cleaning if you have many time series.
Okay, so no humans so far. What is your take on deep neural network with entity embeddings for time series? Proven to work by Jeremy Howard on Rossmann sales competition on Kaggle, for example.
Okay, now I will look stupid because I'm actually watching Jeremy Howard lectures on fast.ai. I like them very much. But I don't remember this point. I remember that he is using Rossmann sales competition, but I'm not sure what are entity embedding. You mean like the other factors to like not only the time series but other information?
So care to specify? Okay.
Yes, sort of. You just take the values where you have, let's say, 10 of them, and create embedding for those 10, and you use those embeddings. You have like, I don't know, 100 embeddings as your parameters in a deep neural network. It was in the newly published Fast AI. It was like.
I was one of them that was watching them even before they were published.
Yeah, me too.
We should probably talk. Okay, so I'll rephrase that question a bit. One of the disadvantages of the time series is that it's just an array of the numbers. Think about that if you have like additional information. If you are trying to predict the sales, maybe you are interested, like if you sell the ice cream, maybe you want to incorporate into your prediction like what was the temperature at a day. Mm-hmm. There's no easy way how to do it with the classical time series method. So one of the advantages of the neural network is that with the embeddings, you can even like, if you have many categories, there is the most of you probably knows. Like the way the people are using from the words, like take the Czech language and just project it to the space with, I don't know, 200 or 300 dimensionality. So similarly, you can take, I don't know, all the information, either other information, or you can use like all these holidays and days of a week and day of a month, because sometimes series theoretically could depends on how many days are from your paychecks or whatever, and use the embeddings to basically select the relevant part for your time series prediction. So it's great. I wanted to try the fast.ai on the Kaggle, and I didn't accomplish that before the talk, which is my fault.
Of course.
Okay, and the last question from the Slido is, have you tried hierarchical temporal memory? How does the prediction compare to other models?
Okay, so the short answer would be no, because I honestly don't know what it is. Could the author give the explanation? What's the hierarchical temporal memory, or do you know?
It's okay to specify, somebody? No specification.
Okay, so that's homework.
Yeah, it's not. Oh, so, I'm sorry. Yeah.
Well, hierarchical temporal memory is neural network from Numenta, and they use two kinds of encoding, which is spatial and temporal encoding, which accounts for different kind of trends in the data, and they put these encoders in a hierarchical manner using particle swarm optimization, so the structure is optimized for the data prediction, and apparently it can predict anomalies and give a pretty good prediction of the data trend itself. And I wonder if you have used it, and yeah, it's a very good framework towards AGI. So
then I should probably look for it, honestly.
Yeah.
But thank you for pointing that. There are many, if you're thinking about the neural networks, there are many things I didn't have really time to mention. Like, for example, for LSTM, it's harder to have longer memory than let's say 100 of time points. So you then need some smart way how to drive the annual seasonality, because you basically have no way how to remember 300 time points. So there are the ways how to do that. If you want to know about that, the people that won the Kaggle competition are really open about their solutions. The first one and the second one can be downloaded on the GitHub, so you can just use the same what they did. And it's definitely worth to read the discussion. Most of I know about neural networks and time series is from the Kaggle discussion.
Okay, thank you. Are there any more questions from the audience? Yes.
Yeah, thank you for the speech, by the way. How difficult it is to predict anomaly. So to predict normal, let's say, data and seasonal, etc., that's nice. But how to predict anomaly, and if it is possible, when the anomaly is starting, let's say, when is the point where you can really predict that some anomaly is coming? Mainly when you clean the data at the beginning.
That's a good question. I have never done that because there was another group at Google that were predicting anomalies. But the time frame the frame I have seen are those Bayesian state time series I've mentioned. When to predict the anomalies, it's not so easy if you are doing this ensemble model, because for the ensemble model you basically have 1 point. And you need, if you want interval estimate, you need somehow bootstrap the errors or something like that. If you really want the statistical model, the Bayesian framework is the easy choice. It's probably possible to do that with the neural networks, but I have never done that. That's yeah.
Yeah, thanks.
Any more questions? No? Okay, thank you very much for the presentation.
Thank you for coming.
That was very interesting.
Finding time to be here.
Okay. So please applause again to Petr. I would also like to thank you, all of you, for coming, because today we have a lot of people here, so thank you very much. Before we start the networking session, I would first of all want to thank to our partners for the support, namely Konica Minolta, Seznam, Rosum, Central European AI Institute, Innovatrix, and also to Impact Hub for giving us this space so we can meet here. I would also like to invite you to another meetup, which will be at the end of March. The talk will be given by Jiří Hana and Rado Klíč, and they will talk about challenges of practical natural language processing. And I also want to invite my colleagues, Lukáš and Markéta, to come here, and please applause to them because they did all of this for you and prepared everything that is related to machine learning. Thank you very much. And so now we can start the networking session. As I mentioned, there are some beers, some refreshments, some snacks. So have fun and enjoy the evening. Thank you.